Okay, this is a walkthrough of P1 and it's June 2015 and it's the foundation paper. You're going to need a ruler, a calculator and a physics equation sheet. Okay, and on this paper it's question 7 only. You're going to be marked for your grammar. So using good English, organising information clearly and using specialist vocab. Right, let's get started on question 1. So, different parts of the electromagnetic spectrum are useful for different methods of communication. Figure 1 shows a transmitter emitting two electromagnetic waves, J and K. So here we can see the ionosphere, we can see a transmitter, the receiver, J drawn in and K just a single arrow. Wave J is reflected by a layer in the atmosphere called the ionosphere. Wave K will also be reflected by the ionosphere. On figure 1, draw the path of wave K to show that it does not reach the receiver. So we're going to draw it on using a ruler. So we're going to follow this line that's already been started. And we're going to meet the ionosphere and then we're going to reflect back at the same angle that it's entered. So if you want to draw another normal line, you can do to work out the same angle to reflect it by. And we can see there that it does not reach the receiver. Okay, remember the examiner is only going to judge that that angle is the same by eye. Okay, it's not going to they're not going to measure it, so just make sure it looks accurate. What is the name given to the dashed line in figure 1? And we've already said that bit there, that's the normal. Okay, this question here would have been a really easy question to not notice and lose those 2 marks there that we could have got. Okay, so it's worth looking for the marks, not the dotted line where you need to write your answer down. So just make sure you don't miss any easy marks out. Okay, figure 2 shows a transmitter sending a signal to a satellite orbiting the Earth. So here we can see L going through the ionosphere and up to satellite. Which type of electromagnetic wave is used to send a signal to a satellite? Draw a ring around the correct answer. Well, it should be a microwave. What name is given to the process that occurs as wave L passes into the ionosphere? Draw a ring around the correct answer. So it's this process here. Remembering a process ends in T-I-O-N, so that's what we're looking for. And in this case, the one that means that that ray there has bent is refraction. Okay. Right, wave J, K and L are electromagnetic waves. What are 2 properties of all electromagnetic waves? They are all longitudinal. They're not. Okay, that means it's like the slinky spring. They are all transverse, so they look like this. That one's going to be correct. They're all mechanical. No, they're not. They all have the same speed in a vacuum. Yes. And just check the last one. All electromagnetic waves have the same frequency. No, they don't, because we know as we look at it, we get a bigger wavelength, so the frequency changes throughout the electromagnetic spectrum. Okay, we've ticked 2 boxes and it asks for 2 in the question. Okay, on to question 2. Okay, figure 3 shows a man using a leaf blower to move some leaves. The leaf blower is powered by an electric motor connected to a battery. Energy transfers take place when the leaf blower is being used. Use the correct answer from the box to complete each sentence. The battery stores something energy which is transferred into electrical energy. Well, batteries store chemical energy. The electric motor transfers electrical energy usefully into something energy. Well, we're blowing, so we probably need a fan inside there. So we're going to use kinetic energy, and the motor wastes energy as something energy and as energy that heats the surroundings. Well, it's not going to waste it as nuclear or electrical, it's going to waste it as sound, because we're going to hear it, but that's not particularly useful. On to the next part of question 2. The total power input to the leaf blower is 750 watts. The useful power output of the leaf blower is 360 watts. Calculate the efficiency of the leaf blower. Use the correct equation from the physics equation sheet. We've got total power input and useful power output. So these are the terms that we need to calculate efficiency. And we can see here, they appear in this calculation here, efficiency, useful power out and useful power in. Okay, so the efficiency equals the useful divided by the total. So the energy useful, energy is 360. We're going to divide that by the total power input, which is 750. Okay, so we've done that straight away using our equation sheet to work it out. So E is going to equal 0.48, and we can times it by 100 if we want. It's good practice to finish it off and multiply it by 100. We're going to times that by 100 to get it into a percent. So it's going to be 48%. So we'll write that down here on our line. Please make sure if you calculate it as a percentage, if you times it by 100, you add the percentage there, otherwise you could lose the mark. Okay, on to question 3. Okay, figure 4 shows a black metal casserole dish that's put inside a hot oven. Food is cooked inside the casserole dish. Energy is transferred quickly from inside of the hot oven through the metal casserole dish to the food. Why are metals good conductors of energy? So we've got because they contain free atoms, because they contain free electrons, or because they contain free ions, and it's because they contain free electrons. Remember that bonding in a metal, you have a row of your metal atoms, and then you have the free electrons floating around outside, and these can move and collide and transfer the energy down through the metal. Okay, so it's because they contain free electrons that makes them good conductors. Why do black surfaces become hot quickly? Is it because they're good absorbers of infrared radiation, because they're good absorbers of ultraviolet radiation, or because they're good absorbers of visible light? Well, it's because they're good absorbers of infrared radiation, because that is the same as heat. Okay, so that makes them hot or become hot quickly. Okay, figure 5 shows a person removing a hot casserole dish from an oven using oven gloves. Use the correct answer from the box to complete the sentence. The oven gloves are good conductors, insulators or radiators. Well, they are good insulators. That's why we use them, so we don't burn ourselves when getting hot food out of the oven. How would wearing oven gloves affect the rate of energy transfer to a person's hands compared with not wearing oven gloves? Okay, so if they were wearing energy gloves compared to someone who's not wearing energy gloves, the rate of energy transfer would be higher. Well, that would mean they'd burn themselves because they'd get hot quickly. The rate of energy transfer would be lower. That looks like it's going to be right. Let's just check. The rate of energy transfer would be the same. No, because there would be no benefit otherwise to wearing oven gloves, and we know that there are. So we're going to tick that middle one there. And it does say only one box. So we've only got one box ticked. What 2 factors determine the amount of energy transferred by an electric oven? So if you're not too sure here, energy transferred actually features on our equation sheet here. And it depends on the power and the time. So if either of these change, it will change the energy transferred. So if that was 2 and that was 2, 2 times 2 is 4. But if power then became 3, 3 times 2 is 6. So that's going to become larger, okay? So the 2 things that determine the amount of energy transferred by an electric oven is power and time, okay? A company has invented an app that allows householders to control the electric oven in their home using their mobile phone. The mobile phone can be used to switch the electric oven on and off. Suggest one benefit of using a mobile phone to switch an electric oven on or off. Well, the idea that they want you to put down here is that you can then switch it on and off remotely or when you're not at home, okay? So you can turn the oven on or off when you are not at home. You could put e.g. at work. And what's the benefit is that the food can be cooked before you get home or for when you get home. Okay, good. Right, on to the next question. Okay, question 4. A can chiller is used to make a can of drink colder. The can chiller decreases the temperature of the liquid in the can by 15 degrees C. The mass of the liquid is 0.33 kilograms. The specific heat capacity of the liquid is 4,200 joules per kilogram degrees C. Calculate the energy transferred from the liquid as it cools. Use the correct equation from the physics equation sheet. So we're going to have a look here. We need to use the energy transferred. We were given the mass, we're given the specific heat capacity. So it's worth highlighting what we've got, and we've been given the temperature, okay? And we can look here, we've got energy, mass, temperature and specific heat capacity. So this is the calculation we are going to use. So we're going to put E equals mass times specific heat capacity times temperature change. So E equals the mass, which is 0.33, okay? And the change, or the specific heat capacity is 4,200 times by the temperature change, which is 15, and that is going to give us 20,790 joules. Put that down here. Energy transferred. Okay. Right, the specific heat capacity of a substance is the amount of energy required to change the something of 1 kilogram of the substance by 1 degree Celsius. Well, what do we know that's measured in 1 degree Celsius? Well, it's temperature. So the specific heat capacity of a substance is the amount of energy required to change the temperature of 1 kilogram of the substance by 1 degree Celsius. Okay, to calculate the specific heat capacity of the material, the mass of the material needs to be measured. State the name of the measuring instrument used to measure mass. Well, it's called a balance. If you put scales, that's absolutely fine. You'll also get the mark, but a balance is the technical scientific term. The back of the can chiller has cooling fins as shown in figure 7. So here we can see the diagram here. The cooling fins increase the rate of energy transfer from the can chiller to the surroundings. That means more energy is lost as heat quickly. Complete the following sentence. The cooling fins are a something colour because that makes them a good emitter of infrared radiation. Well, we know that black or dark colours are very good emitters as well as absorbers. The cooling fins are a dark colour. The large surface area of the cooling fins allows the air around the can chiller to gain energy quickly and rise. So if it's going to gain energy and rise, okay, and then it's going to fall and lose energy, it's transferring energy by convection. Okay, and that's the process where we get this convection current moving round and round. Okay, the energy input to the can chiller is the same as the energy output. This shows that energy is conserved. Complete the following sentence. Energy can be transferred usefully, stored or dissipated. That just means spreads out, but cannot be something or destroyed. Well, that is created. That is literally a specification point just put on here with a gap missing. And again, that emphasises the need to go through your specification for revision. Okay, the temperature of the can of drink decreases while it is in the can chiller. What happens to the temperature of the air around the cooling fins? Okay, so if the temperature of the can decreases while it's in the can chiller, we know that the cooling fins mean that the energy is lost, so the temperature of the air around the cooling fin will actually increase. Okay, as we lose energy from the cooler itself or the can. Right, on to question 5. Okay, question 5. Figure 8 shows a solar thermal power station. So here we can see a solar receiver and lots of mirrors. Energy from the sun is directed at the solar receiver by many mirrors. Suggest one reason why a solar thermal power station is built in a hot desert. Well, there'd be lots of infrared radiation. Okay, so lots of infrared radiation. Right, next bit. Complete the following sentence to describe how the mirrors direct energy from the sun towards the solar receiver. Energy from the sun is something by the mirrors towards the solar receiver. Well, it's reflected. Okay, so energy from the sun is reflected by the mirrors towards the receiver. So we can see here it comes off the mirror, and reflected up to the solar receiver. Okay, heated water is used to generate electricity in the solar thermal power station. Choose the correct answer from the box to complete each sentence. So we've got the words here in the box. At the solar receiver, the water is heated in a something which turns the water to steam. So is it heated in a boiler, a motor, a transformer or a turbine? Water is heated in a boiler. The steam turns a something which is connected to a generator. And hopefully remember our order, you will know that's a turbine. So it turns a turbine which is connected to a generator. The generator produces electricity. A something is used to change the voltage for transmission along power stations, and that is a transformer. Okay, which you can have a step up or step down transformer. Okay, a solar storage power station is a new type of solar power station. It is able to store energy from the sun to generate electricity at night. The solar storage power station can supply a town with a maximum electrical power of 140,000 kilowatts for 15 hours. Calculate the maximum energy in kilowatt hours stored by the solar energy power station. Use the correct equation from the physics equation sheet. So we've been given power and we've got time. So if we have a look here, E equals P times T. So energy equals P times T, or power times time. The power is 140,000 times by the time, which is 15, and that's going to give us that number there. So 2,100,000 kilowatt hours. I'm going to jot that in this box here at the end so they know which answer they want I want them to mark. Right, 5C. A different method of generating electricity uses wind turbines. A student researching a wind turbine wrote the following. Top Hill Wind Farm has 25 wind turbines. Last week, one of the wind turbines generated electricity for only 42 hours out of a possible 168 hours. My conclusion is that all wind turbines operate for only 25% of the time. Give 2 reasons why the student is not correct in reaching his conclusion. Well, he only looked at one wind turbine for 48 hours out of 168 hours. So he really didn't do a lot of research at all. So he only considered or used or measured one wind turbine. Okay, and he only looked at it for 1 week. So just last week it generated electricity for 42 hours out of possible 160 hours. So he was only looking at it for 1 week. So only looking at the electricity generated in 1 week. Give 1 reason why wind turbines do not generate electricity all the time. Well, wind is unreliable, okay? It changes its speed all the time and sometimes it's not there at all. So we can say that wind is unreliable. That's why we would not rely on wind only to generate all of our electricity. Give 1 advantage of using wind turbines to generate electricity compared with using fossil fuel power stations. Well, they do not produce carbon dioxide. You could say they're renewable, that would be absolutely fine as well. So we can say they do not produce carbon dioxide, so do not contribute to global warming. Okay, right, on to question 6. Okay, question 6. Scientists can use the visible light spectrum from distant stars to determine whether stars are moving. The visible light spectrum from stars includes dark lines at specific wavelengths. Figure 9 shows the visible light spectrum from the Sun and from 4 other stars, A, B, C and D. So here you've got your different spectra. So we've got the sun, and we've got a label saying increasing wavelength and blue and red. So think about the Doppler effect, similar effect here. Okay, so with this, we can see that the stars moving further away, or the planets or galaxies, should have that red shift. Okay, because if we look at the wavelength, we can see that the red wavelength is much longer because they're moving further away, and the blue shift, the wavelength is much shorter. Okay, so if we look at these stars, A has the same wavelength as the sun, B has got a shorter wavelength, C a longer wavelength, and D quite a bit shorter wavelength. Which star, A, B, C or D, is moving away from Earth? Well, if they're moving away, it's got red shift, they're going further away, so that's going to be C, because that's got the longest wavelength. Okay. Then this one, how does the speed of star B compare with the speed of star D? Tick one box. The speed of star B is greater than the speed of star D. The speed of star B is less than the speed of star D, or the speed of star B is the same as the speed of star D. So let's compare B and D. So we can see that B has come closer, slightly closer, and then D is even further along down the line here. So D is faster than B. Okay, so B is slower, or the speed is less than that of star D. So we can tick this one here. The speed of star B is less than the speed of star D. Okay, a radio wave is emitted by a star. The radio wave has a wavelength of 150 meters and a frequency of 200,000 hertz. Calculate the speed of this radio wave. Use the correct equation from the physics equation sheet. Okay, so if we have a look what's got wavelength, frequency and speed, we can see down here speed, frequency and wavelength. So we're looking at this equation. Okay, so we've got V, F times wavelength. And we also need to choose a correct unit for our final answer here. So speed equals frequency, 1,500 times the wavelength, 200,000, and that's going to give us 1, 2, 3, 4, 5, 6, and we're going to write that in here. Okay, and the unit we are going to use to measure speed in, so if you think about miles per hour is the common speed you probably think of, so a distance and a time, so we've got meters per second. Okay, meters per second squared is acceleration, so it's not speed, and meters is just distance, so it's meters per second. If you're not sure, try and think, you're calculating speed, try and think of a speed unit that you're more familiar with, like miles per hour, and think about what those two things are. So that's a time, a distance and a time, and that's what we've done there. Okay, right, on to question 7. Okay, question 2. So this is the one we're going to get marked for our grammar. So in this question, we'll be assessed on using good English, organising information clearly and using specialist terms where appropriate. A householder wants to reduce her energy bills. She collected information about a number of ways of reducing energy used. This information is shown in table 1. So here we've got ways of reducing energy. We can install an energy efficient boiler, insulate the loft, install double glazed windows, or install cavity wall insulation. Here we've got the cost to buy and install in pounds, and then we've got the money saved per year in pounds. Use the information in table 1 to compare the different ways of reducing the energy used. Your answer should include some calculations. So it's told us to compare, which is really important, and we need to put some calculations in there. So if we're comparing, we have to comment on the same feature on when we're looking at different things. So for example, if I was comparing a mouse and an elephant, then I might say an elephant has larger ears than a mouse. So it's that larger, ER, that's the comparison, that comparative statement, okay? So we need to make sure that we are comparing properly in our answer. So what we're going to do is we're going to start off by looking at which one saves the most money per year and which one saves the least money per year. So, and then we can compare the cost to buy and install the most and the least as well. So we can start off by saying that the installing double glazed windows is going to save us the least amount of money per year. Whereas if we buy an energy efficient boiler, that's going to save us the most energy per year. So we're comparing the money saved, but on different ways of reducing energy. So an energy efficient boiler would save the most money per year in pounds, whereas the double glazed windows would save the least money per year. Okay, so there's a direct comparison we can see on the same feature. All right, on the next one then, we're going to compare the cost to buy and install in pounds. Okay, so the one that's going to cost us the least to install is the loft insulation. The one that's going to cost us the most to install is the double glazed windows. So these aren't sounding particularly effective at the minute, are they? Amount of money being saved is the least, and it's actually going to cost us the most as well. So the double glazed windows cost the most to buy and install, whereas the loft insulation costs the least to install at £400. Okay, so it might be worth putting in some data, although they do want calculations. We could quote some information as well from the table. Okay, so we've got two clear comparisons there, same feature, but now it did ask for some calculations, so we need to have a little think about it. Now, one of these things, when we're looking at energy and it costs to put something in and the amount of money saved, we probably need to calculate some payback time. So for example, if we look at the loft insulation, it's going to save us £200 per year, but it costs us £400 in the first place. So the payback time here is 2 years. So in 2 years, I will have paid back the money that it's cost me to install in my savings. That's quite an efficient method, okay? Whereas if we look at these ones and we divide the numbers, this is going to take us 6.25 years to pay back. The installing double glazed windows actually going to take us 100 years. 120 divided by 12,000, it's going to take us 100 years to pay that back. Now, that's realistically not going to be paid back in a lifetime. If you're going to put your windows in when you own a property, then you've got to wait 100 years until you've paid back. That's not going to happen in a lifetime, okay? And the last one is 2.86 years, so not much more than the loft insulation, okay? So we can see that in terms of payback time, the loft is going to have the least payback time, whereas the double glazed windows are going to have the longest payback time. So we're going to compare payback time now. So the loft insulation has the shortest payback at 2 years. Now I am going to give the numbers because then they can see that I've done the calculation to work out the payback. So what I've done is I've done 400 divided by 200, no sorry, other way around, 200 divided by 400, and that will give me my 2 years payback time, okay? And I can say whereas the double glazed windows, that's my next sheet, have the longest payback time at 100 years. Okay, so what I did there was 120 divided by 12,000. Okay, And if we wanted to write them in order, then you could do as well to show that you've calculated it. So we could talk about, you could list them if you wanted to. So you could talk about the ranking of them. So you could say loft insulation, then cavity wall insulation, then energy efficient boiler, and then double glazing. That would be absolutely fine as well if you wanted to list it. I think what we'll put here is that the longest payback time at 100 years, which you would not pay back in a lifetime. Okay, because that's sort of an extra point of information there. So in terms of cost effectiveness, it's looking like, and money saved, it's looking like the loft insulation is probably the best bet here, but we certainly would say that more than likely double glazing is look like the worst solution. Okay, so you could say that I think that the loft insulation, or probably a tie between the cavity wall insulation and the loft insulation, because that is going to save us quite a bit of money, but this is actually going to save us more. If you look at that's actually saving, or actually it's going to save us less. That's going to save us about a little bit less, isn't it? Whereas this is saving us, half the amount it's costing us to buy and install. It's saving us quite a lot of energy there, £200 a year in terms of savings. Energy efficient boiler is going to save us £320 a year, so a bit more. However, it is going to take us 6 years to pay back. So I think we'll stick with loft insulation as our most energy efficient, I think, and cost effective way of saving money. So I think the loft insulation would be the best for cost effectiveness, and the double glazing the worst for cost effectiveness. Whereas we said, didn't we, the boiler, so if we have a look at the boiler, install energy efficient boiler actually saves us a little bit more money per year, 6.25 years to pay back. So we might say that actually what we're thinking is that the whereas the energy boiler, although it takes 6.25 years to pay back, is the most energy efficient solution. Okay, so I think now we've compared enough things, we've done some calculations as well, and we've given an overall conclusion at the end. Okay, increasing the amount of insulation in the house affects the total U value of the house, and we want the lower U value here. So what is meant by the term U value? So we need to think about the definition that we know for our U value. So the U value tells us how effective a material is as an insulator. Okay, so how effective a material is as an insulator. Okay, and how is the U value affected by increasing the amount of insulation? Well, it decreases the U value. Okay, so the U value is how effective a material is as an insulator, and it decreases the U value when we increase the amount of insulation. Okay, on to question 3. Question 3. A householder monitored how the air temperature inside his house changed over a 2-hour period. The householder measured the temperature every 15 minutes. Figure 3 shows how the temperature changed with time. So here we can see the air temperature in degrees C and the time in hours along the bottom. And you can see it's a spiky graph. The householder used a digital thermometer to measure the temperature. What would be an appropriate resolution for the digital thermometer? Resolution means the smallest degree it can measure. So the best resolution would be 0.5 degrees C, because that is the smallest number it can measure. The householder's results are shown on a line graph in figure 3. Why would it not be appropriate to use the results or to plot a bar chart? And that's because the data is continuous, it's not categoric in any way. And if you think to ISAs, this is often mentioned. So the data is continuous. Okay, you could put not categoric, but saying it's continuous is fine. Okay, on to 3 part B. The householder's heating is controlled by a thermostat. The thermostat switches the heating on when the temperature decreases below a certain temperature. At what temperature does the thermostat switch the heating on? So if we look back at the graph, we can see that it comes up and then it drops down and then it goes up again. So it's going to be this number down here where it's switching it on. So we can have a look across. Okay, so it's this bit here and it falls in between 20 and 21, so 20.5 is going to be our answer here. Use figure 3 to determine the number of minutes the householder's heating was on between 7 and 9 o'clock. So if we have a look, it goes up and then it drops down, it goes up and then it drops down. So I'd assume the heating is on at this point here and then gets switched off, and on again here and gets switched off. So it's going to be on from this point to this point here, and then again here until this point here. Okay, so it's these areas that we need to try and measure. So from there to there is an hour, so that's half an hour plus another half an hour. That makes 60 minutes or 1 hour. We know our time in minutes, so it's 60 minutes. Okay, right, 3C. The householder read the following extract from a newspaper article about reducing energy use in the home. So decreasing the temperature setting on your thermostat by 1 degree C will reduce your heating bill by 10%. On Monday, the householder set his thermostat at 20.0 degrees C and recorded the energy in kilowatt hours used to heat his house. On Tuesday, the householder set his thermostat at 19 degrees C and recorded the energy in kilowatt hours used to heat his house. Table 2 shows the results of the householder's investigation. So we can see that the thermostat setting in degrees C, 20 and 19, and then the energy in kilowatt hours, 8 and 7.2. So we can already see that at 19 degrees, it's reduced the amount of energy used in kilowatt hours. The outside temperature was the same on both days. Give one reason why this is important. Well, it's a control variable, so if we can control it, we can make a good comparison. So we can say that the outside temperature is a control variable. Okay, so it needs to stay the same. Right, explain how the results shown in table 2 support the extract from the newspaper article. Justify your answer with a calculation. So let's go back and read the newspaper article one more time. It says that decreasing the temperature setting on your thermostat by 1 degree, which is what they've done here, will reduce your heating bill by 10%. So all we've been given is energy in kilowatt hours. Now you should be familiar with the fact that the cost to you on your bill is the amount of kilowatt hours you've used multiplied by the cost per kilowatt hour. So the more kilowatt hours you've used, the more money you're going to have to pay. But has this decreased by 10%? So what we need to do, we need to work out the difference. So 8, and we can do it down here, 8.0 take away 7.2 is 0.8. So that's the difference, but is it 10%? We need to divide it by the total, which is 8. Okay, and what we get here, then 0.8 divided by 8 will give us 0.1. 0.1, if we want to make that into a percentage, we times that by 100. Okay, and that's going to give us 10%. So it has reduced our heating, it's reduced our energy by 10%. So we can give that as our answer. However, we just need to explain it slightly, and we can say the bill depends on the energy in kilowatt hours as the cost is the number of kilowatt hours times the cost per kilowatt hour, or you could say unit would be absolutely fine. Okay, so that there I've explained it, shown it's 10%, so I've showed that it's right, and I've justified it with a bit of a longer answer there. Okay, last part of question 3. The statement in the extract is not valid for all situations. Suggest why? Well, we might use the heating more on one day than we do on another day, so we can't say this is consistently correct all the time. So we're going to say that the heating may be on for more or less time than anticipated. And we'll say because it's worth 2 marks, we need to put a because in there really, because it is sometimes colder or warmer than anticipated. Okay, or we thought was going to happen. All right, so heating may be on for more or less time than anticipated because sometimes it's colder or warmer than anticipated. Right, on to question 4.